Be mindful of this as you tap on jars of insects or fish in aquarium. Let's review your life cycle of a star. So you can do this without your notebook. All stars, all planets, comets, everything begins in the nebula. Once the hydrogen starts to fuse into helium, you're going to be a protostar. If that protostar does not have enough mass to make it to the main sequence here, it's going to be a brown dwarf. If it has too much mass, that it fuses through its hydrogen much too quickly, it's just going to go. And of course, there's all kinds of dwarfs in this category here, and all kinds of giants over here. Because I'm having you memorize these 20 items, I'm keeping it pretty broad. If all of your protostar material is able to reach a high enough temperature to begin fusing the hydrogen into helium, you will be, as we mentioned, a main sequence star. This is the low mass side, and on the low mass side we will have a helium flash once all our hydrogen has been used, and that helium flash will then result in a red giant. You'll then begin to collapse upon yourself, your temperature will rise, and you'll be a yellow giant. And then you'll have a massive explosion, resulting in a planetary nebula and a white dwarf. And that's the low mass side. So the low mass side. And you'll want to be sure to label high mass side. So once you fuse your hydrogen to helium on the high mass side, you'll be a yellow giant. It's different than this yellow giant. Then you'll begin to actually cool down, so you're a red giant. Then you will begin to warm up again, become a supergiant. Then you have a massive explosion, a supernova. There's nothing more explosive in our universe outside of a supernova than a Big Bang nucleosynthesis expansion. And then this is the low mass side of a supernova result, or the high mass side of a supernova result. We looked a little bit here with neutron star and supernova remnants. And that's what we've done so far. We just have 3 more items to complete. Before we dive into these final 2, we need to get a little bit more physics under our belt, and that is with the theory of relativity by Albert Einstein. Now, this is how some people react to thinking about relativity, or the thought they might have to learn about it. Every time I see a math word problem, it looks like this. If I have 10 ice cubes and you have 11 apples, how many pancakes will fit on the roof? Answer, purple, because aliens don't wear hats. Now, we are certainly going to give you the Einstein theories of relativity simplified. The major difference between what I would do with students at the high school level versus a college class is at the high school level here, you probably haven't had calculus. And so we're going to have a few times where it might be frustrating to just say, well, the evidence is in the calculus, in the mathematics of it. And by the way, calculus was originally called the calculus. So we're going to give you the simplified version of the science behind the theories of relativity. It's important to bear in mind, as Einstein stated, that education is not the learning of facts, but the training of the mind to think. We mentioned a few times in this class, when you are famous, make sure your family publishes the childhood photo of you that you would like shared with the world. There's a young Einie. And this is during the war when he worked for the U.S. Navy, his time card. So maybe a relic from your job will appear in the National Archives. And the Google Doodle on the 14th of March in 2003, which signified the 124th time his DNA made a revolution around the sun. Can't say perspective enough in astronomy. In June of 1907, Dear Mr. Einstein, your application for the doctorate has not been successful at this time, and as such you are not eligible for the position of associate professor. While you posed an interesting theory in your article published in Annales de Physique, we feel that your conclusions about the nature of light and the fundamental connection between space and time are somewhat radical. Overall, we find your assumptions to be more artistic than actual physics. Sincerely yours, Professor Wilhelm Heinrich, the Dean of Sciences at the University of Bern in Germany. Oh dear. Persistence, people, persistence. Let's begin. Item 1 on page 30. What is the first principle of the special theory of relativity? Well, it goes something like this. Your physical description of reality is the same regardless of the constant velocity at which you travel. Your physical description of reality is the same regardless of the constant velocity at which you travel. Item 2 asks you to describe an example, and I'll describe an example here as you jot down that your physical description of reality is the same regardless of the constant velocity which you travel. Let's say you have a ruler, 30 centimeter ruler, and as I'm standing still and I look at this ruler, I will measure it to be 30 centimeters. So my physical description of reality, I have this real ruler in my reality, and I measure it to be 30 centimeters. If I were to start walking across the classroom floor at a rate velocity of, say, 1 tile per second, I would measure that ruler to be 30 centimeters as I paced out. 1001, 1002, 1003. Every second, it would still appear to me as 30 centimeters. If I got into a car, and being a passenger, of course, safety first and always, and I am driving or being driven at a rate of, say, 50 kilometers per hour, I'm going to look at my ruler, and I'm going to measure that ruler to be 30 centimeters if I'm traveling at 50 kilometers per hour. If I got in a train, I travel 150 kilometers per hour, I'm going to measure that handy-dandy ruler I seem to carry everywhere with me to be 30 centimeters. If I got onto an airplane, I travel 400 or 500 kilometers per hour, and I have my handy-dandy ruler with me, I'm going to measure that ruler to be 30 centimeters because my physical description of reality is the same regardless of the constant velocity at which you travel. Maybe I go into a rocket and I travel tens of kilometers per hour, or tens of thousands kilometers per hour. I've got my ruler with me, never leave home without it, and I look and I measure that ruler to be 30 centimeters. If I get going at speeds close to the speed of light, I will look at my ruler, I will measure it to be 30 centimeters. If I take the measurement of my big toe and I'm moving at a constant rate, I'll always measure the height, width, length, whatever I measured of my toe to be the same. If I remain calm in all these situations, my heart rate, my breathing rate would be the same, regardless of the constant velocity at which I travel. So my physical description of reality is always the same, regardless of this constant velocity at which you travel. So item 2, give you example the ruler. You can choose anything, your height, your mass. Maybe you carry a shorter ruler with you, a pen, a pencil. And it doesn't matter if you're walking very slowly, running, sprinting, in a car, in a train, in a plane, a rocket ship, traveling as the energy from the sun is light. You will always measure that item to be those dimensions that you originally measured before you started moving at a constant velocity. Second principle of the special theory of relativity is that nothing will travel faster than the speed of light. Nothing travels faster than the speed of light. And the symbol for the speed of light is a lowercase c. And the c represents constant. The speed of light in a vacuum is constant, 300 million meters per second. We've mentioned in this class, if I take a baseball, I throw it at the speed of light in a way that I'm able to orbit the Earth, not hit myself in the back of the head, that baseball is going to go around the Earth just over 7 times in the frame of 1001 second. So the speed of light is constant in a vacuum. And the second principle tells you you will never measure anything to be greater than the speed of light. And sometimes this is difficult for humans to be told that there's limits. We've looked at how the minimum possible temperature of anything is 0 Kelvin. Temperature, remember, is the rate at which particles are moving, average kinetic energy. And so if you have a Kelvin of 0, that means your particles aren't moving. And so being told that the speed of light is the maximum something can travel is sometimes something as humans we don't want to think of as there's limits in our universe. Now, to help you try and appreciate that we really don't want things to be moving at the speed of light outside of a vacuum situation is because, let's say we have a marshmallow. It's got a mass of about 10 grams. If I throw this marshmallow to you at a rate of just under 99 and 99 hundredths of a percent the speed of light to hit the Earth, what would happen if we run it through Einstein's relativistic equation here? You're going to end up with the energy that is the equivalent of a few dozen good-sized hydrogen bombs. One marshmallow, I chuck it at you, very close to the speed of light. The equivalent of a couple or 3 dozen healthy hydrogen bombs, healthy in size, are going to cause mass destruction. The marshmallow's incinerated, you're incinerated, anything in its path is incinerated. So a vehicle that we want to make that travels at the speed of light, not so much. That's a one-trip voyage. So when we see these sci-fi vehicles traveling at warp speed, speeds greater than light, not so much. That's why it's science fiction. So the increase in mass is the reason that Einstein says matter cannot travel faster than light. The mass increases with velocity until the mass becomes infinite when it reaches light speed. An infinite mass would require infinite energy to move, so it's impossible. Mass and energy are different manifestations of the same thing. Einstein's equation of E equals mc squared means an amount of energy that is equal to amount of mass times the speed of light squared. And that's what enables the release of a huge amount of energy from nuclear explosions. Now this is the very first time in Einstein's notes that he wrote this famous E equals mc squared equation. And sometimes we look at things like c squared and say, wait a second, that is c times c. That is greater than the speed of light. Well, one of the ways I look at it is think about the equation is indeed E equals mc squared. It kind of rolls off the tongue much easier than if I were to set c squared is equal to, I'm just going to have this energy divided by, maybe energy, divided by mass. So I've just put this over to here through division, leaving this by itself. And then I want to get the c by itself, so I would take the square root. And so we're saying the speed of light is the equivalent of the square root of energy divided by mass. And so you'll see, rolls off our tongue a little easier with this E equals mc squared. We're not saying in this equation that something is traveling at squared the value of the speed of light. And we're going to give you a little insight into how it is that nothing can travel faster than the speed of light, thanks to the great physicist of Clifford Johnson.
Physicist Clifford Johnson at a bicycle track, where a tennis ball will compete against a beam of light.
If I throw an ordinary object like a tennis ball, I can throw it at a given speed, and it'll go a certain distance.
This is the path of the tennis ball as Johnson throws it while he's standing still. It lands roughly halfway down the track. Next, he'll throw the ball again, but this time from a moving bike, with different results.
If I throw the tennis ball at that same speed while riding the bike, it'll go faster because it's the speed of the tennis ball plus the speed of the bike, and so it'll go further.
Compare the two tosses and the difference is clear. The ball goes faster and farther when thrown from the moving bike. It makes perfect sense. But now we put light to the same test, using the bike's headlight instead of a tennis ball.
If I'm standing stationary and I switch on the headlight of the bike, that beam of light that comes out of the headlight comes out at the speed of light. No other speed but the speed of light.
Suppose the beam was slow enough for us to actually see its motion down the track. We mark its position just a brief moment later. Next, Johnson switches on the headlight at riding speed, and the unexpected happens. In that same moment of time, the light travels exactly the same distance as before.
Unlike for the tennis ball, you don't add the speed of the bike to the speed of the light. The speed of light remains the speed of light.
The two light beams travel the same distance because light speed is constant and independent of the source's motion. It may fly against intuition, but it is a fact of nature.
And it's that flying against intuition that is in direct conflict with Newtonian physics. Newtonian physics is kind of how you and I operate and function throughout the world and thinking about how things move. And we'll take a look at how the second principle of the theory of relativity is in conflict with Newtonian physics. Let's first look at a very classic approach where perhaps the baseball is being thrown at a velocity of 10 meters per second. If we were to then say, all right, situation 2, the ball is thrown at 10 meters per second, and the person who is throwing the ball is also running at perhaps 5 meters per second. If we were going to describe the total velocity, this total velocity, I'll just put VT, V total, is the ball, 10 meters per second. Down here, if I were to look at the situation of what's the total velocity, well, the ball is moving at 10 meters per second, and the ball thrower is moving at 5 meters per second. So we add those. That is a total of 15 meters per second for that ball because the person was running 5 meters per second. A very classical way in the world of physics. Newtonian is how we describe it. If we come around to thinking of Einstein, let's say that the baseball is thrown at a speed of light. So velocity here is c, speed of light. The total velocity is the speed of light. If in this situation the ball is thrown at the speed of light and the person is running at the speed of light, your classic way of thinking about this would be the total velocity is c plus c. Now, not c squared, we've been saying E equals mc squared, but c plus c is 2c. What Einstein is coming along and advocating and saying is nothing travels faster than the speed of light. Einstein would take the independent motion of the light and the independent motion of the light of the person moving and the ball moving and say that the total velocity of this ball thrown at the speed of light while moving at the speed of light, or we should say speeds close to the speed of light, is just c. From the top to highlight. The most typical way, if we say this ball is moving at 10 meters per second, we say the ball has a total velocity of 10 meters per second. If we throw the ball at 10 meters per second while moving at 5 meters per second, the total velocity is 15 meters per second. If we switch it up to light, we throw the ball at a speed close to the speed of light, the total velocity is c. if we throw the ball at the speed of light as the person moves at close to the speed of light, we do not say that its total velocity is 2c. What Einstein is saying is that the velocity is c. You'll never record something to move faster than the speed of light.